guest, we have Nathan Faggian. He joined the Centre for Australian Weather and Climate Research in the Australian Bureau of Meteorology to work on the development of a national forecasting system. But now he's working in a weather services branch on developing bushfire predictive services. So I ask you to welcome Nathan and his talk, Evaluating Fire Simulators Using Docker, Dask and Jupyter Notebooks.
Thanks, everyone. It's extremely difficult to follow a really good keynote, so you'll have to give me a little bit of traction on my talk today. I don't know if people have realised this, but I think, it feels like every time I come back to PyCon, about a third of the audience is from the Bureau of Meteorology. So I can see a whole bunch of them sitting over there. I work in the weather services part of the Bureau. It's composed of a few bits. I thought I'd just throw in a slide to basically say what the severe weather program is that I work on. So I'm a part of severe weather services. That's part of a program. We basically define forecast policy and services that go out through other divisions and are developed by other divisions to provide services to the public. The part of the severe weather program I'm in is actually responsible for tropical cyclone services, the fire weather program, that's where I sort of fit. But also severe storm services. This is actually just a small amount of what we're responsible for, by the way. Today, the talk I'm going to give you is about fire predictive services and how we're looking at fire simulators, particularly fire spread simulators. In Australia, there's 4 that are sort of used by the different fire agencies. And the Bureau is interested in how these simulators perform, because we have a sort of an obligation to provide weather information to these service providers so that they can help provide really good warnings to their public. So the fire agencies, for example, in Tasmania use a simulator called Prometheus to simulate fires. That's come from Canada. It's actually because a lot of the forest and things like that in Tasmania fits pretty well with the Canadian forest environment. Their models work really well in Tasmania. CSIRO's started to develop some fire spread simulation models. There's a framework called Spark. We're looking at that too. There's also Phoenix, which is particularly popular. It was developed by the University of Melbourne. That's used in just about every part of the fire service around Australia, except for Western Australia, where they have their own different model called Australis. That was developed by the University of Western Australia. It's basically a slightly different approach to modelling the spread of fire models. So yeah, I'm in severe weather services. I'm not a research guy or a systems guy, but I dabble. So, why are fires important? Well, there's a few obvious reasons, I think. One, they impact the community, okay? In fact, in the last couple of years, you could argue because of climate change and things, we've started to shift towards an environment that's conducive of huge wildfires. An example I've got up on the screen here, which was graciously provided by David Roththorn, is a photo of the Blue Mountains Lithgow fire. Just some interesting facts. That fire burnt for about 10 days, burnt 55,000 hectares, and on a single day, it ran more than 25 kilometres. Okay, that's terrifying. I mean, if you were in this township here and you looked at that mountain, you'd probably run in the other direction as quickly as you could, right? So we need to get better at determining when the weather's bad, how likely is it that an event like this will occur. The Bureau's in the game of providing the weather intelligence to the fire agencies, and the fire agencies are in the game of picking up the simulators and the weather intelligence and saying, hey, everybody, we should evacuate that town, or at least we should be thinking about the possibility of events like this occurring. I've got a nice little video that I've picked up from Catalyst, which sort of hammers home again why it's important to start thinking about fire behaviour. So I'll put it on now, and hopefully the audio and everything is good. I apologise for some of the language in this presentation, but you'll understand why the guy says the thing that he says. Oh. So let's see if I can make this thing play. Doesn't want to. Just one sec. If everybody could get off the internet, that would be great. Oh, someone did.
It's just after 5 p.m. At the bottom of the mountain, directly below the Clarks, a fire has engulfed St Andrews. With the ground cleared around his house, Jim Baruta feels safe enough to arm himself with nothing more than a video camera.
How safe can you be? I mean, I think if anyone's got a chance, it's someone like me. I haven't got the trees up to the house and things like that, so I thought I'd be fine. But then when the fire came, it was nothing like I'd expected it to be. You could hear the noise. It sounded like trains or jets coming towards you in the distance. It kept getting louder and louder. It's like all the trees were exploding from heat. People say it's the leaves, the heat of the oils in the leaves and the eucalypts, they just go off, and it's like gas going off too. It's just burning like crazy.
The gases from the eucalyptus trees are escaping so quickly that they race upwards, mix with the air, and explode. The fire is feeding itself. The flames 4 times the height of the 20-metre trees.
Once it starts climbing up the hill, it just starts accelerating even faster and faster. It just builds up this momentum, and it's just eating everything in the way. It was just like you were in the middle of a hurricane. It was a hurricane, but it was on fire. There's all this debris going everywhere. Anything that was not bolted down or something was in the air flying around. It was going to hit you.
A fire tornado has now developed, ripping through tens of acres in seconds. At well beyond 1,000 degrees, it makes an oven of earth and air. This firestorm can now kill from 200 metres.
I stood behind the brick pillar out there, and there's no way, if you put your hand out like that, it would have been burnt. It was like putting your hand in front of a furnace. And then I realised that there was a problem with the air that I was breathing. I wasn't breathing properly.
The fire is less than 300 metres away. Jim's in danger. Not of being burnt to death, but of suffocating. But he's got a backup plan.
And I thought, I've got to get out of here, and I've got to get to the bunker. I had to step out into the storm with my back to it, and it was all hitting me on the back. And I walked past the side of the house, into the bunker, and I shut the door. Whatever was going to happen was going to happen, and I couldn't stop it.
The fire sweeps over Jim, and he survives.
Jim was very lucky, and possibly also extremely stupid for putting himself in that environment. So I'll just flip over to the next thing. So that video, I think, should give you an impact of why it's important to understand fire behaviour. I mean, there were some things in there that we can't currently still define. So a fire tornado, how does that form? How do we describe the physics that's around a fire tornado? If you have all these different types of heterogeneous fuels, like different trees, they burn at different rates, they generate, actually they can generate their own weather and they can influence the fire again. Fire simulators are about trying to pull some of the knowledge that we've developed over the last 50 or so years into an automatic, framework. I guess you could think of a simulator as a bag of fire models. And automating the process that we go through to effectively sort of war game what's going to happen. If the weather's bad and a fire starts, where will it spread? How quickly will it spread? How many people will it influence? fire simulators model characteristics of fire spatially. They're still pretty simple. And there's a sort of development of the science that's seeing us want to include more weather in how the simulators actually work, so that, for example, in the future we might have a numerical weather prediction model that actually burns fires inside it. But at the moment we're sort of at the point where we have a numerical weather prediction model generating weather and a simple simulator generating fire spread outputs. In the figure here we can see for a particular fire, I think this is around Creswick, where the developers of Phoenix actually operate out of. If we start an ignition point at t equals 0, which you can sort of see that little blob in the centre of the Google Earth picture there, if we let that run for 6 hours, you can see the impact of the simulation basically spreads a few kilometres. The red points are properties of fire called spotting. So basically when a fire burns, it can throw fuel up into the air, and that fuel's on fire, that propagates down a couple of kilometres perhaps, it starts another fire. So yeah, there's this process in there that the rate of spread of a fire is actually full of a bunch of complex things that are actually very difficult to model. Sorry for the bright white slide, but I'm guessing it'll wake you up. The underpinning mathematics and things for the simulators at the moment isn't actually that complicated, okay? There's a few schools of thought around how to model the propagation of a fire front. Some of the most successful ones are quite simple geometric models that basically say if you know what the type of fuel is that you're surrounded by and the rate at which it burns, you can step in a particular direction. And you sort of keep on updating that step over time and you get your simulation output. The West Australian model uses cellular automata, which would be familiar to a computer crowd. That's a pretty popular approach for modelling the rate of spread of diseases and things like that. With fires, they just have a probability of ignition type thing where they say, okay, you're going to propagate into the next cell if you've got enough fuel to burn, for example. That's one component of simulator. There's lots of components. It's taken people decades, literally, to come up with the underpinning models that plug into these things. Very much a case of standing on the shoulders of giants. One of the most influential guys in this space was called MacArthur, who basically burnt a large chunk of Canberra to try and come up with these geometric models. I won't say any more about MacArthur. Brilliant man. So this talks about evaluating fire spread models. What's an evaluation? So an evaluation is obviously a process of picking up something, looking at it and making an assessment. In this case, it's an assessment of quality. The Bureau of Meteorology doesn't actually run simulators itself. They're run in the fire agencies, and we've been contracted to do this work. So we have to go out and talk to the fire agencies and understand what they define quality as. Okay? And there's a lot of questions you ask when you do that. One of the key ones is, well, what's your forecast process? How do you actually use these simulators to make decisions? They're decision support tools. Okay? So we've consulted with emergency services. We sort of understand the questions they ask of simulators broadly. And we're at this point now where we're starting to ask ourselves questions like, how do we measure these things? How do we define a measure of quality? The figure on the left here is just an example of a forecast process that happens in Victoria, where they have an automated system that generates fire simulations. They have a co-located meteorologist. They have a fire behaviour analyst, and they try and come up with predictions of where the fire is going to go. They basically work through this. So in the context of the Bureau and what we've been sort of engaged to do, what is an evaluation? Well, an evaluation for us is, given our understanding of quality and these metrics that we should go and calculate, given that we know that we've got 4 different simulators in Australia, how are we going to go and evaluate all these metrics? And well, it's a computational task, okay? You've got 4 black boxes, essentially, which are the simulators. You've got a bunch of fire events, which are known, the significant events that have occurred in the past. And what we want to do is figure out the sensitivity of the fire simulators to its inputs and the quality of the outputs that result from varying those sensitivities. So the figure on the left is just sort of like a explosion of simulations type diagram that says if you wanted to understand the sensitivity, for example, of this Phoenix simulator to wind direction change, a common approach is that you perform a sensitivity analysis. You just take the wind input and you vary it between a particular range. That generates a collection of outputs, and you figure out what happens when you twist this knob at one end to the output at the other end. And so with that output at the other end, you have to compare it against something. The gold standard at the moment for us is line scans, so that's literally a plane flying over the top of the running fire. At a particular point in time, we get a snapshot of where the fire progressed to. Its extent is defined. People literally draw polygons and say, this is what the shape of the fire was at this time. So we take the simulator, we run it to that point in time, and we compare what the simulator generated to what we observed. And we calculate a metric. And there's a lot of metrics. So this is a programming conference. I'm going to get to some of that eventually. So, you know, what supports an evaluation, okay? Well, I think there's three components. And underneath all of this is people, okay? There's a lot of communication, understanding about what quality actually means. But I think the key things, and I'm really happy to be involved in this session of talks because I'm going to talk about reproducible science, okay? One of the key things is a reproducible environment, okay? We're going to be doing these experiments, we're going to be sort of kicking these fire simulators and generating outputs. And I want people to be able to repeat those experiments after the fact. If there's new case studies or something like that, it should be easy for people to increase the sample size for our analysis. You know, obviously, there's some software that's associated with this. We have to make an evaluation framework or a tool that someone can kick to generate the outputs, generate the graphs, generate the reports. Sort of underpinning all of this is the tool, the Jupyter Notebook that we use as sort of our framework for reporting, I guess. I sort of use it as a workflow execution tool. That's how I describe it to people at work. It's an interactive report, but it can execute code on clusters and things like that. So that's how I've sort of been selling it, the Bureau. The figure on the right shows my sort of 10,000-foot view of what's actually going on. We have these Jupyter notebooks which describe workflows. They're just experiments. The experiments have to do things with simulators. Simulators are these horrible heterogeneous blobs, right? They're implemented in different programming languages. I didn't mean to say they're horrible. They're not actually horrible. They're beautiful. They're fantastic things. But from a software point of view, they're all coloured in different ways. They use different pieces of technology. One might be a web application. One might be a .NET application. The other could be some GPU-enabled binary thing that you don't have much control over. So we took Python and we wrapped that as the throw rug over all of that. That gave us a way to execute the simulators. And then we used Jupyter as an environment to kick that. Obviously, because we have a need to execute these things many times, if we're performing a sensitivity analysis, we have to have some compute power that sits underneath that. It's just a cluster of computers. And that's comprised of Windows virtual servers and Linux virtual servers. You could plug a supercomputer in there like NCI, for example, as well. And then we generate lots of output because we generate lots of simulations. And the simulations are just stored at the moment on disk, but they could go to a database. There's a lot of simulation output, as you can imagine. There's also a lot of curated weather data that we have to collect so that we can feed the simulators and run them. So now I'm going to start getting into the technical discussion, and I'm going to expose myself as not much of a Docker expert, okay? And I thought the best way to do that was to just go directly to the Docker website and pull some of the information off there as a summary. And then to say I use it and it's fantastic and it's great. And I'll give you an example of how I'm using it. But I asked myself the question last night, how do you describe what Docker is to people? And I Googled it and I found a few terms where people were calling Docker containers lightweight virtual machines. And then I found a whole lot of hate around using that terminology to describe Docker. So I decided to go straight to the Docker site and pull out what they say. I look at Docker and this process as just an enabler, right? So Docker is a tool that I use to completely pin down my evaluation environment. So what does that mean? That means, well, I'll show you what it means. It means on GitHub, for example, I probably should show you what I mean. Just let me escape out of this. On GitHub, I can share my environment with people so that if they want to replicate the experiments I've performed, they can start up my Docker container, which contains all the libraries and all the things that I need to run the simulators, in a very simple to use way. Now, the environment that we use is a composition of a bunch of containers. I guess in IT lingo, there's this thing called orchestration, and we basically take a bunch of these Docker containers and we connect them up and they provide services to us. The tool we use for that is Docker Compose. I'd encourage people to have a look at this if you like, but essentially all it is, it's a way of us describing exactly what the services are that sort of underpin the evaluation framework and the pieces of software that support it, so the libraries. To get into more detail, I'm happy to do afterwards. It's basically a simple use of a CentOS I don't want to say virtual environment, CentOS-based environment with the Anaconda Python distribution that sets up notebooks and things. So, Dask is also in the title of this talk. I use Dask. Once again, I'm not an absolute expert. I use a subcomponent of Dask. So the thing that I make the most use of is the distributed component of Dask. The way I sort of look at Dask is it's a tool that enables you to scale up and scale out. Okay? So if you've got some computation that is particularly amenable to shifting onto some cluster, and simulators are, because simulations are independent of each other. So I use Dask for the simple task of task farming. Basically, I get each of the simulators, wrap them in a little function, throw them off to the cluster goes and calculates that independent thing, stores the result, and I can pull it back. I've got a notebook which is an example of that, so I will just escape out of this and give you a quick demo of what Docker is actually being used for and how we're using Dask. So I describe Dask as, and the combination of Dask and Jupyter notebooks as a web-based distributed execution environment, which sits pretty well with people because a lot of these things seem really complicated. If you go to a supercomputer and you've got to learn how to use a job scheduler and all of that, that's a bit daunting. Whereas if you just opened up a web page and clicked play a few times, that's not that daunting. So the technology that sort of underpins this, these Docker containers, we've got a Docker container for a notebook server. We've got a Docker container for a scheduler, which is the thing that controls all the Dask jobs. We've got a bunch of distributed workers. They go and talk to these simulator containers because simulators are these heterogeneous things. They'll have different environments that they need set up. And then we've got some Docker volume containers. So all this stuff is all orchestrated with Docker Compose. It all glues together. You can start and stop it. You can run it on Windows. You can run it on a Mac. You can run it in Linux. So just a typical example of what I'm doing without going into the detail of the actual simulator execution is a pretty straightforward workflow of loading some data, cleaning it, analysing it, and storing the result. Okay? And so this Dask sort of delayed decorator that they've provided, or delayed function, allows you to create a graph that you can basically apply to the composition of functions and then execute. So it's quite simple. Okay, this isn't particularly inspiring in terms of what we're doing here. We're just sleeping a bunch, okay? But the idea is you define a couple of functions and you chain them together. And then you use this thing called delayed to turn that chain of functions into a graph, which then gets sent out to your cluster and calculated. Okay? It's as simple as that. To give you an example, if we take that chained workflow, right, which consists of 500 of these load, clean, analyze, store, sort of sleepy functions, I guess, and we throw them off to this thing called an executor. So in the context of an executor, that's something like a similar interface to the multiprocessing concurrent futures type interface that exists in Python, right? You can throw these functions along and you get this thing called a future. Future basically says, I promise you that I'll go and calculate this function, and it does that using this distributed sort of machinery. Distributed has this really nice interface. It allows you to look at the progress of your work in notebooks. If you go to the distributed website, you'll see some of this stuff. If we run it, something should pop up. You get these sort of progress bars, give you an idea of what's shuffling its way through the queue. Behind all that, there's actually also a really nice interface based on this bokeh plotting library that you can use to see what's happening. You know, mileage varies with this a little bit depending on how big your workflow is. Often I'm confronted with questions like why I use open source. One of the really good examples is I was using Dask to do simulator execution. I ran into a brick wall. Basically, one of the simulators was a Windows simulator and I couldn't set up Dask workers. So I contacted the author and I said, cross-platform workers don't work. I can't connect. And I got this horrible exception. I don't know what to do with it. Within about 5 minutes, it was fixed. So, you know, at the time, I was the lone wolf developer, I guess, pulling together all of this framework. All of a sudden, it felt like I had a team, and it was great. So I've used this as an example to my managers to say, well, hey, you know, there's some real benefits to using open source software and having access to this environment. In real terms to them, it just means they got some work done for free and they love it. You know, for me, I like the idea of being involved in the community, and that's really great. So let's flip back. There was a comparison of Dask to Spark. You know, someone asked a question about this the other day. I pulled it straight off the website. People can read the slides if they want. I just look at Dask in comparison to Spark as a much, much, much simpler framework to use. You can pip install Dask, okay? You know, and you can pip install distributed, and you can just set it up in like a heartbeat. It takes no time at all. My experience with Spark basically boils down to a word counting exercise that I played with ages ago, and that's it. So I'm not going to say any more about Spark. We use Jupyter notebooks. We use them to generate reports. We use those reports and presentation material that sort of comes out of the documents at conferences and things like that. It's the Swiss Army knife for us. You know, essentially in terms of the simulator execution environment, it's sort of a front end to distribute code, to distributed code. So it's how we kick the simulator executions off. It's how we make sure they're running. We've actually paid a person to convert Jupyter notebooks into Word documents automatically. We have a tool to do that, by the way, which is fantastic for us because we write lots of Word documents. We do a lot of methods development. I'll escape out of this and just give you an idea of what happens. So, you know, we do things like visualize data in notebooks. We look at fire scars. We mess around with them. This is all interactive. May or may not zoom in. Well, that zoomed in completely the wrong direction. But anyway, the point is we do a lot of work in notebooks to look at the outputs. And sort of the path that we have is we do a lot of sort of bespoke analysis work that eventually becomes do-it functions in modules that then reduce the amount of content that we have in the notebooks. Which is probably not a bad way of going. It also has to go through, you know, a testing path as well. So that notebooks, I sort of think, sometimes are like the Wild West. Like you can basically open them up and put anything in there and it's fantastic and you get some result. And I think that disconnects people from good software development practices. And yeah, I'm encouraging people not to do that in my team. So if we go back, pretty close to finishing. Yeah. I know the next few talks are about reproducibility and science and all of that. And I just wanted to say a few things about where we're going next with the evaluation project in terms of technology, right? I really strongly feel we're following the recipe for reproducibility. You know, I want someone in a year or 2 years after I'm working on something else or thinking about something different to be able to pick up my project, just push play and regenerate the results, okay? There's a few bits of technology that support that. One piece of technology is GitHub, for example, having the code out there and open and interrogatable by external people is a good thing. It's never a bad thing. I'm going to stop, I promise. The other thing that we have to think about using is a reproducible environment, making that available to people. I use Docker Hub. It's a free service. It's really good. Another service that we make use of, mostly because it's free and it's fantastic, is Circle CI. So any of the unit tests that we've written for the evaluation software gets funneled through Circle CI. It's all wrapped into our build process. And that's it. Thank you.